Good afternoon, everybody. Welcome to this Tech at Lunch session on distributing electricity in industry using direct current. Prior to diving into the presentation, I'd like to point out that for everybody, the cameras and microphones are by default muted and turned off during the presentation. You can post questions in the Q&A chat box. They will be answered at the end of the session, where we can have a discussion, and be advised that we will record this event and share it at a later moment so that you can look back, but also when you talk that you know that you're being shared online afterwards. Given that, let's dive in, because in the coming half an hour, 20 to 25 minutes with my presentation, I'd like to take you into the world of direct current electricity distribution, DC, tailored towards industry. And this is the results of a project that has been running over the past 3 years at Flanders Make and Flux 50 in Energyville, together with the industrial partners listed below. And these are the main takeaways, the lessons we've learned by playing around with it. And to start the session, I'd like to sketch the scene a little bit, because industry today, and as the target group, of course, industry today is facing a number of transitions. And I selected 3 which are most relevant to the context of today. The first one is a transition towards more and more sustainability, and sustainability that can be the case on 3 elements, or mainly in 3 elements: the environmental sustainability, to lower your footprint and to make certain that the materials you use can be reused, etc. Economically sustainable models, really a new way of thinking about economics, and on the same time making sure that sustainability is achieved in an economically feasible way. And there is also a social element, but that's less relevant today. At the same time, there is a lot of talks about energy. It's a very hot topic, pun intended, today. For certain, and main elements in those energy transition are affordability, meaning that you could still pay your bill, which is very relevant today, but also the security of supply. Security of supply is typically something that's being tackled at a national level, or even at a European level, but for each company it's very important. Everybody needs to be certain that their energy is actually available or delivered when it is required. Otherwise your production stops, and that's of course non-desired. And then finally, also the climate plays a very important role in that energy transition, lowering greenhouse gases, lowering primary energy consumption, and so on. And so there is a clear link with sustainability there as well. I think it's already clear from the get-go that these elements, the energy part, is very relevant in the context of DC energy distribution. But there is also Industry 4.0, the transition towards this new way of producing things where everything is interconnected, where your elements, the things you produce, can be mass customized. A customer orders something which is tailored to his needs. And the fact that everything is interconnected is to play to a certain flexibility need that is there to enable mass customization. And there is also an energy part in this Industry 4.0 element, because everything needs to be reconfigured, everything needs to be flexible. It makes sense that also the energy provisions are flexible, and that is not the case today. So this is kind of the background for the story that I'm going to tell today, and I'm going to come back to this slide later on to see how we can address these elements when we talk about DC for energy distribution. But now for the more core of the presentation, the industrial grid, which distributes the energy. And I'm going to try to explain to you very high level what an industrial grid is. It brings energy from the left of the figure from the electrical grid. Typically, we're interested in electricity today. It brings them to loads, and that makes sense. You want to use the electricity to produce a certain element, to do something useful. And it's the load in which most people are interested in. That can be a machine that produces something. It can be a fan that cools material. It can be heating to change material properties, and so on. So the right part is where everybody is interested in, but it starts from the electrical energy on the left. And the electrical energy transfers through a power distribution system in your plant. It's distributed towards all the devices that require it. And then very often today it is converted. It is converted from traditionally AC, which is supplied by the electrical grid, alternating current, towards something which can be actually used to drive a certain motor, and the motor drives the load. And over the past few decades, there have been lots of research on this chain. Most of the research events can be mapped on this chain, where we have new motor types, we have better power electronics, we have better control, which align the load with the power electronics. There's a lot of activity ongoing. But the actual power distribution, the part that we're interested in today, has seldomly been tackled. It's a very standardized system. It's very rigorous. All the components are standardized. All the players are known. Everything is fixed. You make your connection. You hire a certain integrator to build your grid, to make the design choices. It's basically adding up all the electricity requirements, laying cables, and that's it. It's not subject to research. There is very little progress in the power distribution because it has worked very reliably for a very long time. And it's exactly that power distribution that we're going to tackle today, because I'm going to propose a different way of distributing power. And to make that bridge, I'm going to do it again a bit graphically. On the right, you see a more detailed view about machines inside a factory, where in red you have your motors, which do the work, and in green you have a DC bus in the middle. And more about that later, because that's of course what it's all about. And then in another type of red you have the alternating current with a plug drawn next to it, which is fed by your network. And you will see that graph change later on. The elements that are in an industrial grid today are what I have drawn on the right. Lots and lots of machines which do the work. And inside those machines, you find variable frequency drives. You find speed-controlled motors, torque-controlled motors, which perform a certain action. Today, there are also still grid-connected induction motors, can be a very effective means of having something rotate, but the transition towards speed-controlled or overall controlled motors is ongoing ever less. And then controllers. There are controllers everywhere, computers to interface everything. Everything is connected. All the machines need to be controlled. All the converters need to be controlled. So it's filled with controllers. Those are the main consumers of electricity in the industrial grid today. Over 2/3 of electricity in the industry is consumed by machines or by electrical motors. And then, as mentioned in the previous graph, there is a distribution board which connects to the machines, which supplies the machines with electricity. It connects them to the low voltage transformer, and the low voltage transformer is the place where you connect to the main power supply to the grid of Fluvius, for example, in Belgium. But that picture, that traditional picture of transformer, distribution board, and then a bunch of machines is actually changing. Today, more and more companies are interested in producing their own electricity for security of supply, for affordability. So they're adding, for example, photovoltaic panels on the top of their plants, or they're even installing their own windmills for the very big ones. So there is the generation of electricity in the factory. Additionally, we have set up the transition towards electric mobility is ongoing. Electric mobility can be for your staff, it can be for your for the goods which are transported around. It can also be autonomous vehicles traveling on the work floor. They all have batteries inside. They all need to be charged. There's also converters required to charge those batteries. So it's a completely different load, especially the electric vehicles, the ones which are used for personal mobility, but all the others as well. And then there are batteries these days. More and more companies are interested in installing energy storage on their premises, again, for security of supply and affordability, to make sure that you can have the energy when you need it. And if you look at my drawing, there is a schematic battery drawn inside machine A and machine B. That's actually because most of machines also have a little bit of storage on board. It can be just the capacity of the capacitors on the DC bus today. Some machines have most will have some capacitance. There can even be a bit of storage included for fault right through, but it's very local and it's very minimal. But today we're really thinking about installing batteries for the entire factory, or for a certain part which is very, very critical. And all these elements are still connected to the distribution board, to the low voltage transformer, and are fed from an AC grid. That's the situation today. But when you actually take a look what's inside all those elements, Well, inside the variable frequency drives, I already mentioned it, there is an internal DC bus. It's a necessity to operate machines at a variable frequency. The grid-connected induction motors, they are often transitioning away towards variable frequency drives, and very often it would make sense to install a power electronic converter only to do flux control, for example, or to better control those machines. So they are an opportunity for DC. It's not a necessity, of course, but they are an opportunity for DC. And then everything that's controlled, whether it's a control element, all ECUs, all computers, well, de facto they are DC, but they are low voltage DC. So they are at a different power level than the drives. But then these new loads, the photovoltaic panels, for example, well, inherently they are DC powered, and the converter which connects the photovoltaics to the grid will have an internal DC bus as well. The electric vehicles, they are driven by DC. They have a battery inside. The battery powers the entire system, so they have by de facto an internal DC bus. And if you would fast charge them, you would even hook up to this internal DC bus directly. And the same goes for the batteries, as batteries are inherently DC. Well, if you would connect them to something, there would be a DC bus as well. And I think you already see the commonalities here, and now have a close look at the picture on the right. Doesn't it make more sense then to just hook up all these devices to a common DC bus? And that's what we try to do. So connect all the internal DC buses, and that eliminates a lot of common components. It means that you can centralize your AC to DC conversion, and it means that you have to distribute your direct current over your factory. But also it means that almost every node, every component which is connected to your grid becomes controllable. Controllable because everything is connected via power electronics, and power electronics need control to be able to operate. So you could implement energy management to control or to exploit the degrees of freedom that you have in the controllable elements in your grid. And in order to exploit flexibilities, of course, you first need to identify degrees of freedom. So plenty of machines will have regenerative braking, for example. Just reuse that energy, make sure that you can reuse it in AC. In an AC grid, that's not always a possibility. In a DC grid, that's inherent. But there are other degrees of freedom, for example, when you start up a certain machine. There's more on control on the next slide. And then finally, the integration of batteries certainly is much more effective in DC. You do not need, you eliminate a lot of conversion steps. So typically, if you would connect a battery to an AC grid, you would need an AC-DC and then DC to DC converter to connect the battery. You can eliminate the first part, but when the power that you store could be, for example, from a machine. And so in that case, it would go from the motor over a converter to the internal DC bus, back through a converter to the grid, and then from the grid to the converter, the AC-DC, and then the DC-DC converter, and then the battery. So you can imagine that you can eliminate a lot of conversion steps when charging and then discharging. It needs to travel all the way back, discharging the battery. So effectively, or definitely in the case of batteries, the integration is much more effective when you do it on a DC grid. And I already mentioned that from the point of view of control, there is a lot of interest, not only by the fact that you can control it, but also by the fact that you should control certain elements, such as your batteries. They need control, otherwise they don't know when to charge or discharge. So I have a specific slide on control, on what to control. So for example, for machines, you could offset startup peaks only by a few seconds in some cases, or by a minute or so. It's not a necessity, it's an option. But if you know about your startup peaks and you act on your startup peaks, then you can offset your startup peaks, and you can just limit the amount of power that is required in your grid to flow, which is an inherent saving. If you require less power, your components can be downscaled, etc., etc. So if you have that option, then it's definitely worthwhile to consider it, but you need control to do that. In industry, there are a lot of oscillating loads, and you could desynchronize them. You could put them out of phase so that they can cancel each other out. And it basically means that when there is a certain dip in energy consumption or even regenerative flow, power flowing back to the grid, then another machine can use that power. And it's ideally you control that you have the optimum there. And finally, in the case of availability, in the case of security of supply, you could disable non-critical loads when there is a certain issue to feed critical loads. So typically there is a lot of inertia rotating inside a machine. If that machine is directly connected to a DC grid, you could stop one machine, one motor with a lot of inertia. You could take the energy out of that inertia and use it to power a more critical element in your grid, which perhaps needs a bit more time to safely stop in case of an emergency. Now, for machines, that's one thing, but for these new loads, it's even more apparent. For the new loads, you can increase self-consumption of renewables by tuning your loads to the power that's being generated or the energy that's being generated, and that, of course, can save you a lot of money. You could also do coordination of the charging elements, so coordination of the EV charging or optimal charging of the battery that is installed in your grid. And so there are much more elements to be gained for these new loads when you implement control. Why hasn't that been done then before yet? Why am I presenting the results today and not 5 years ago? Well, there were 3 elements which are missing. There's a bunch of practical experience missing, how to do it, how to go about, which components to use, when is it safe, when is it stable, which communication do I need to assemble this control, etc. There was also a quest for a proven business case. What are the actual numbers? What are numbers to expect? Which requirements do I need to set? How feasible is it for my case? And then there is the fact of standardization. Everything is standardized in AC. There are limited standards for DC. So I'm going to tackle the first 2, the practical experience with the outcomes of the project. I already gave you a preview. The standardization is an element which has not directly been tackled, although our partners were active in standardization committees, but it's an open question still, which not one party by itself can solve. So from the practical point of view, what did we do? Well, we built a DC grid. We built a system which is fed from the AC grid still, and the main source of energy is the AC grid, but it's centrally converted. It's used to generate a DC bus voltage, and that DC bus voltage is distributed over a distribution system, over cables towards different machines of different brands. So we installed, in this case, 4 different brands of machines. They're all fed from a central DC bus. They all use different communication protocols. We all connected it together. And the main result here is that it actually works. It's feasible to have this miniature DC grid up and running. And with that, we're actually one of the first in the world, if not the first in the world, to install a DC grid using just off-the-shelf available components today. So this is a map of all, in principle, DC grids in the world, maintained by an external party, all the activities on DC, and there are very, very few focusing on industry. Actually, there are only 2 here and at Fraunhofer in Germany, or in Germany in general, which are targeting industry, and we are the only ones who have used off-the-shelf available components. There have been no specific design. We just used the components which would already be there in AC, except for the distribution board, of course, that needed to be built, but that only used off-the-shelf components. So we are a special case and a very relevant case of DC distribution. Now, more on the lessons learned in a few slides, because I want to combine them with what we learned from control, because on this grid, we also implemented real-time optimal energy management. Real-time optimal is debatable if that's required. Energy management, I already indicated the advantages. So what did we do? We used a model of our system to combine it with predictions on the load, and so we could implement various load profiles to emulate a certain industrial case. We could use the predictions, the knowledge on that load profile, together with a certain objective and a solver to optimally distribute the energy in our grid on a real-time basis. That objective is, of course, very important, so it could minimize the losses, or it could minimize the overall cost, or it could minimize peak power, or do a combination of everything at once. So there are multiple ways you can use this energy management. And an example is the graph shown here, where we did a bunch of things at the same time. So we are charge sustaining load sharing with power constraint in feed. I will take you through those words one by one. Start from the right. So in the case here, there is a certain load profile, which is the blue line, and that blue line cannot be fed from the main grid. So there is a power constraint on the main connection to the grid in our case. So a battery needed to provide the additional energy required, which is then the load sharing part. But of course, when you discharge the battery to compensate for a certain issue, then you also need to charge the battery again to make sure that you can keep doing that forever. So in this case, the algorithm learned that when there was less energy consumption, that it could charge so that it could compensate for the peak and discharge there. And that's the yellow line is then the actual power delivered by the grid, and the red line is the power provided by the battery. So in this case, we set up a system where a battery is optimally used and can be used to compensate a certain issue with the grid, in this case, the power in-feed, which was insufficient to provide power to the load. So what did we learn from trying all of this? Well, first of all, that communication is not a necessity. You can have a functional DC grid without communication. You could even have some form of energy management without communication, but it is very, very much recommended. And also, most of your machines and things which interface with the grid will have a form of communication on board. Typically field buses, Profinet, Ethercat, what have you not. These can be interfaced and these can be used to establish communication between all elements. Of course, that can be costly or take some time to implement, but it does offer benefits with regard to control. So communication is not essential, but it is very much recommended. Then, of course, we had to build this grid. Building means purchasing components, finding components which can distribute the power. And actually, in the industrial world, there is not an established set of suppliers, but from the photovoltaics world, from the marine world, and from the automotive world, there are a lot of suppliers out there who are already supplying components which you could use to build an industrial DC grid as well. And some brands are also familiar in industry. So, for example, Phoenix Contact and Schneider, they're taking steps in providing more and more components, also targeted for the industry. There are many, many more brands, some of which listed here, brands that we use to build this DC grid. So the components are actually quite available, albeit not to the level that AC components can just be taken off the shelf in your local Home Depot. Now, when it comes to the drives that we had to interface, our main focus was on electrical drives, so the combination of power electronics and machines. Actually, all the drives which we purchased, which we used, they were designed to be used in an AC case and they have an internal DC bus. We could feed them directly from the internal DC bus. That is because most drives these days have the option to have some kind of a minimalistic DC distribution when you stick to one brand. But of course, when you combine multiple brands, it becomes something different. So we had to make some software changes. Most of them were there to bypass AC-related faults. But in the end, we were able to interface all these drives to a DC grid, requiring only software changes. And from that, we learned that it's actually feasible to use material which is already out there today to construct a DC grid. When you would attempt something like this yourself, be advised that there are over and under voltage limits when these drives go into error. Those are very important parameters to monitor and to write down that you're right there in the middle. And that middle point, that ideal voltage level for us was somewhere between 650 and 700 volts DC. And when you look at standards where everything is going, if you look at the papers and the material that's out there, this is more or less the voltage level that the industry, or that in general the world is working towards. Will be in the vicinity of the 650 to 700 volts DC. Now, there, of course, were also some challenges that we had to fix in order to get the system up and running, but things which we feel are still challenging today. One of which is the earthing. Of course, everything needs to be safe, which means it needs to be isolated. It needs to be safe to touch all the different elements, and earthing is a very important element there. And earthing is still a tricky topic. Now, there is isolation monitoring available to monitor what is happening. In our case, it can be an IT grid, for example, but then you really need isolation monitoring. So you need to keep track of the status of your system with respect to the earth. That's something to keep an eye on. Safety is solved today with fuses, but of course that's not the ideal case. An ideal case would be breakers, and there are brands working on breakers. For example, ABB is working on breakers for DC, which can be installed in an industrial or residential case, but they are not available for purchase right now. But we tackled our safety, our short circuit protection, for example, with standard fuses, and they are widely available. And then finally, the stability of the system is something to think about, is something to consider. But it's okay. You can analyze your available capacitance. You need to keep an eye on that to make sure that your system is indeed stable. And we had in our project we devised some tooling to support you in that should there be any issues. But it's a solvable issue. Now those were the practical experiences. We also had some results based on measurements, based on simulations, based on best experiences from industrial partners and so on. And I try to list the most important results for you here today. But there is a very high dependency on the specific case for which this is calculated. And so bear in mind that these numbers will vary for your case. But we made a significant, or we are certain that we can make a significant saving on the peak power which is required to feed your system. An guesstimate would be up to 30% savings. Of course, also the number of power electronics that you require is a lot lower. So in most obvious cases that you eliminate half of the conversion steps and change it with one centralized conversion step, but that means you need a lot less power electronic components. So you save on that. And you also save on the cables that you need. So you can play around with how much copper you actually use or how much aluminum you actually use. But most obvious case is that you need 3 cables for AC and 2 cables for DC, and you just need 30% less copper. And those are the savings with regards to the CAPEX. But also when you operate the system, it will be a lot. There will be savings. So you save on conversion losses and on distribution losses. Conversion losses are those by the power electronics. So you eliminate conversion steps, so you save on conversion. And the distribution losses are losses in cables and losses in transformers. You also save there because the quality of the grid is much, or the voltage is much higher. So you save overall 10% on conversion losses, 20% on distribution losses. Again, very dependent on the system. And these are savings on the losses. So it depends on the, your overall energy savings will depend on how much losses you have in the first place. Now, of course, because you centralize the conversion, you can make it much cleaner. So the total harmonic distortion will be a lot better in DC case on the side of the point of common coupling. So where you connect to the grid, of course, and the same goes for the true power factor. And that's fully by choice actually. And so in our case, it was 94%. And then finally, the availability we shortly discussed, and AS stands for ancillary services. So also the fact that you can provide more services towards the grid will be a lot better in the DC case. It's basically by design. Then when we come to the original slide on which I started, I mentioned these 3 changes, these 3 transitions that we're going to. Well, when it comes to sustainability, well, we can offer increased efficiency, we will save on energy, but we will also save on components. In that case, we're tackling a bit on the environmental side and on the economic side. And so both are very relevant, and their DC can really take a step in the right direction. When it comes to the energy transition, of course, there is again the increased efficiency, but also, as mentioned, the integration of renewables is a lot more effective, which improves your affordability. And your resilience with storage is also increased because of energy management, and that implements the security of supply, but also the affordability. And then finally, because you can implement energy management, you can cope with all the flexibilities which are required for Industry 4.0. And at the same time, you can also feed back data on your energy provisions, which is very interesting to do all the elements which are relevant in Industry 4.0, as, for example, anomaly detection. You could also do that on the energy data. So overall, technically, I think it makes sense. Strategically, I hope I also indicated to you that it could make sense to look at DC. Economically, it should also make sense. The numbers are there and we save both on CAPEX and OPEX, but that is very difficult to predict for any case out there. The components are becoming available and most of them are available today, and control is advisable. Those are the messages to take home today. And overall, for me, that means that DC distribution in industry is actually feasible. But there is one but. It's still not the standard solution. So it seems we have a bit of a chicken and egg problem when we want to discuss next steps. And to solve that, I think everybody should be on board with this, because at some point it will actually be there. So for machine builders, I think it's very important to consider the fact that you could feed your machine from a DC grid. it would be really relevant to implement, but of course the savings are there for the people who purchase your machines, except for the fact that you could also have coordination between your machines, and there you could offer some immediate benefits for yourself or for your customer by already considering this DC option. For component manufacturers, it remains very important to focus on these missing elements, primarily the breakers, but also standardized connectors, isolation monitoring, etc. These elements which are still hard to find. And then for integrators, I would advise that they start assembling knowledge about this. I think a lot of knowledge is already out there, but it really seems like this is the next step towards electricity distribution. So it's important that they know their stuff. And then finally, for the ones who have to pay for all of this, the people who own the factories, it will be really important to do a cost-benefit analysis. And my prediction is that the ones which have a very high energy cost today, the ones which already have a bunch of power electronics, or for those for which availability is very important, that they will transition towards DC faster because they simply have more gains to be made. And be advised that there is a difference between brownfield operation and greenfield operation. Now, in the last minutes, I move to my last slide. In order to help with this business case evaluation, we have invested on a rapid evaluation tool in which we can use your case, your load cycles, your situation, your grid layout, and calculate with our tool these numbers that I showed earlier for your situation, so that you can make a bit of a trade-off between the benefits and the downsides. The downsides you should be able to take a first step on that with this presentation, but the advantages will have to be tailored towards you. So should you be interested in discussing this further and discussing the overall picture further, but discussing this your case further, then feel free to contact me at my email address or via LinkedIn or via any of our account managers or business developers at Flanders Make. And with that, I would like to conclude the presentation part and open the floor to any questions, should there be some remaining still. Thank you for your attention.
Okay, thank you, Jeroen, for the clear explanation. We have two questions which are kind of the same, so maybe it's best to try to combine them. I'll read them one by one. So the first question is, how do you deal with the DC voltage drop across long DC buses and cables? And the second question, which is kind of a bit of the same as the voltage master in this example, is the IFE operating on its own? What about larger grids with multiple infeeds or multiple controllable loads? Is there one central controller somewhere, a single point of failure? And what about distributed control and stability?
Yeah, so indeed, both linked questions and both very relevant. So overall, to me, that question translates into how does this scale? And to that, we built a very small grid, but we actually devised a much bigger grid. And the industrial partners in this project, of course, had a much bigger grid in mind. And so actually the idea was that our storage elements, for example, our storage elements and our infeeds could be distributed over the grid. But in that case, you really need energy management. And you could implement distributed control, but there are other ways to do this with a master controller. But it basically boils down to your energy management algorithm that you choose and your stability, the way you devise stability. So we had primary, secondary, and tertiary control in our DC grid, which allowed for the fact that you could have multiple active front ends feeding the grid at different points, or you could have multiple storage elements, and those storage elements could compensate for the voltage drop at certain elements. So there are ways to solve this, particularly how to deal with the DC voltage drop across long DC buses and cables. We did not have a detailed study on this, so I do not have a detailed answer for you, but indeed multiple infeeds could work. And also in DC, it's more or less the same in AC. In AC, you would also have voltage drops, so you would also install compensators or up your voltage to cope with these challenges. Overall, you have no reactive power in AC to compensate for that, to compensate for those issues. But in DC, you have in general just less current flowing around. So maybe the same power, but less current, because there is no harmonic distortion on the DC grid, at least not by the definition as is standardized. There is of course some noise on the channel, but there is no reactive power. So it's mostly purely the pure active power which is flowing on your grid, and that also helps, and overall the voltage drop is lower because there is less current. So I hope that that answers the questions more or less, but it's definitely, both of them definitely are subject to further research as well.
Okay, thanks. One more question, and then I think we're already a little bit over time, so we can conclude this session. But what will or can be the future voltage levels for industrial and residential grids?
So that's a question which is very tough to answer. There is a multitudes of looking at the picture of voltage levels. So the most apparent one is standardization. If people take a decision somewhere, which I would strongly advise that is a certain voltage level, then we just will have to go with the flow. But right now, most of the power electronic, most of the things which are happening in power electronics are actually fed by the requests from the automotive sector. So when you look a couple of years back, then the industry was driving the need towards drives and power electronics. Right now it's automotive, and in that sense it makes sense that the industry would eventually follow the steps which have been taken at automotive, which means that right now power electronic components are rated for 800 or 1000 volts. It's going up towards 1200 volts or even 1500 volts, but I'm quite certain that we will stay below 1500 volts because of the standards that are out there today. And I think for a long time we will still have to deal with the AC grid. Well, have to deal, it's not a bad system at all. But the AC grids will provide 400 volts AC or sometimes 690 volts AC. And so then the rectified AC voltage will also have an impact on the feasibility of your DC, on your DC bus. So that also determines the voltage level. But right now it seems that around 700 volts, sometimes 750, sometimes 650, sometimes 700 itself, or 735. There are a lot of different suggestions. It seems that for the time being that's really the right voltage range to be in, and I see this only going up.
Okay. There is one last question which might be also interesting, so I suggest to make this really the last question. As the common DC voltage range is quite limited, between 650 and 700 volts, won't we be replacing the AC-DC conversion by DC-DC conversion in practice, which introduces new losses?
So to first clarify where that 650 to 700 volt came from, that was the voltage range in which we believe that most of the standards will work, or in which most of the components will work. Actually, our grid operated at a much wider range. We could go higher and we could go lower. I think we could go up to the standard rectified AC voltage, which would be 570 or something, and we could go all the way up to 800 volts. So the range of the system was wider. So to clarify that. But then to your actual question, won't we be replacing AC-DC conversion by DC-DC conversion? Well, actually, if you look at how converters are constructed today, they are a combination of AC-DC plus DC-DC in the case that a different DC-DC converter is required. So indeed, there will be plenty of DC-DC converters out there today, but they are already there. They are just hidden in the same converter package. And so in the case where you would need a DC-DC converter in a DC case, very probably you would have a DC-DC converter today combined with an AC-DC conversion step. And so in that sense, you still save on conversion steps. But I must note that for DC grids, it's very important to not only focus on the conversion losses. DC grids are not only about efficiency. Efficiency are only a very minimal gain, but it's really when you look at the entire picture, if you look at all the possible savings, when you consider control, when you consider peak power, when you consider harmonics, when you consider unbalance, there are a lot of different elements out there, and they all are a small piece of the puzzle, and they're all a small piece of the gains that can be made. And when you add them all together, it's only then that you can be really convinced about DC. If you focus only on one particular element, quite probably it will not make sense for your case.
Okay, thank you, Jeroen. So I suggest we close the Q&A session here, and I'll leave the word to you to finish the session.
Well, thank you all for attending. We're 10 minutes over time. I think that's still within the academic 15 minutes. I thank you very much for your attention. I hope that you found this interesting. From the replies I got in the Q&A, I think that was the case, so that's very good. And I believe really that this could be the next thing, the transition which we have set forward. So I look forward to continuing on this topic with all of you at different events. Thanks for attending.